Okay. Hello, everyone. Uh, Welcome to the week 6 of RecSys Learning Book Club. Today, we'll talk about a data processing and counting recommender. In today's talk, basically, we discuss two chapters, uh, chapter 7 and chapter 8. Uh, just small introduction. So, my name is Rohan Singh Rajput. I'm currently working as a senior machine learning engineer at Headspace. Uh, if you want to know more about my work and this book club, please you can connect me on LinkedIn. So agenda. So we will record these chapters. So if you are not comfortable, please you can turn off your video. Uh, we will the agenda of this book club is that with first 5 minutes we'll talk about the introduction and book details. In the next 30 minutes, we'll discuss about our learnings from the book. In the next 20 minutes, we will keep it for discussion. And the last 5 minutes, we'll keep for wrap up and next chapter. I will record this session. So the first 30 minutes will be recorded uh, and the discussion won't be recorded. So you can uh, talk during those discussion. So about the book we'll be discussing in this book chapter is Building Recommendation System in Python and JAX. This book written by Bryan, Bischof, and Hector. The reason we chose this book because it contains all the advanced topics in recommendation system. It's highly practical oriented and it's written by industrial professionals who have experience building real-time recommendation system. Uh, so just uh, completing the chapter 7 from the last time. Chapter 7, we discussed about integration testing of recommendation system. Now we'll discuss more about different processes in building large-scale recommendation system. One of the process is called observability. So observability is a way to understand what is uh, going on in our software stack. It helps us to uh, monitor and also uh, audit our system and to understand that if something goes wrong. There are two important elements in observability. One is called spans and another is called traces. Uh, we can see them as a two dimension of a call stack where we have like some services running and the sequence of those services called as trace. So let me enable my pin. Okay. So we can see that we have like here 5 services, service A, service B, service C, service D, service E. And the time one particular service runs is can be treated as span. And the trace is that like uh, uh, the sequence of the services, right? Once we finish service A, then we'll trigger service B, then C, then D, then E. Uh, this this the way we structured our call stack here in form of span and trace gave us a higher level visibility of our system, and that can help us to observe our system how our each of the processes are working. uh, up, as we can see there are like several sometimes we these services can have sequential dependency. That means that if we are doing like some kind of data pull and then we are doing like a model building, then we are doing applying some business logics and all those other steps, we have to make sure that like these dependencies are met and these services are start one after another. Some of the services can run in parallel, and for that we can understand that which service take what amount of time. So the goal of observability to understand that how our system is behaving under different type of situation. Uh, it usually help us to understand that what is uh, the amount of delay if some service has over other, or if we have like some kind of delay in particular call. We can diagnose our system behavior by uh, seeing the spans and logs. Uh, we For one of the example given in the book, that like suppose we have one particular instance where we are collecting neighbors from our collector step, as we discussed previously. In the collector steps has like lower response than other services. We can check the spans and traces to figure out which process is taking most amount of time. And in such cases where we do not have so for example, this is your recommendation system, and you're sending your recommendation to your client, and your client could be anything. Like for this case, like let's say you have a mobile application, and you have some service level agreement, some SLA, that you need this recommendation within like let's say 10 microsecond or 10 millisecond. Now, if that SLA doesn't meet and your service does not respond in that case, you should have some kind of fallback. And in our cases, most of the time we use fallback as a MPIR system. So what is an MPIR system? As we discussed, these are like most popular item recommendations. So suppose you want to showcase a personalized movie recommendation to your user, but you are not getting personalized recommendation because of some issue with your system. Then what we'll do, will try to call your fallback, and in the fallback you will send the most popular movie to your user. By that, like you can silently fail, and your user can still get somehow relevant recommendation because this is a global popular movie. So observability can help us to avoid those kind of problems, and we should always have like such kind of timeout and fallback mechanism to have a smooth user experience. Now, there are other methods in evaluation and production system. We have like two type of problems. Like one, what we know as slow feedback. Is the slow feedback means that some of the business KPIs may not directly correlate it with the uh, machine learning metrics or model metrics. So what do we want to say here? That suppose you have e-commerce website, and in the e-commerce website, your goal of your business is to increase in revenue, right? And you create a metric that like more number of sales uh, correlate to more increase in revenue, right? So your model is optimizing for higher conversion. It wants to convert and sell most number of items, but we did not incorporate returns of the item, right? Because returns of the item hurt revenue. So your model can suboptimally sell a very viral product which are not in high quality or very low in price, but later user realize that like these items are not good and they are returning those items. But once they return those items, uh, in hindsight you did increase your revenue by selling most of your items, but you were not able to uh, incorporate those returns, which actually hurt your overall revenue. So we have to use like several proxy metrics to understand that aligns with your business metrics. So rather than just relying on increasing revenue, uh, we have to use some other metrics like overall customer satisfaction with the sales, or some kind of metrics that can truly reflect our business KPI and also optimize our model metrics. Similarly, we would like to understand that how the distribution of our model metrics change over the time. And one of the example there is that there 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 could be instances where your one particular categorical feature have uh, different distribution scores or affinity score in training and then in inference. So suppose you have a model M which has some kind of distribution D in your training data, but when the same model goes in production, and because of some lack of feature or change in like feature density, it produces a new distribution D2. And because the distribution has been changed from D1 or DT to D2 or DI during the inference, this can hurt your overall model performance, because the model was optimized for a certain distribution, and while the features are changing during training and testing, training and inference. So during the training, we used to have like some kind of feature T, and during inference we have like a feature I, and because of some features are missing, the distribution of feature I is not same as distribution of training, and that results in different output distribution of of the same model in inference while in training. To avoid such problem, we can use several techniques. One of the important techniques discussed here is scale diversion, which can help us to understand the divergence between observed distribution and expected distribution from training. So what we can do, we can actually take a scale diversion from like our training data to our observation, like our inference data, and try to understand how much divergence is there. And if the divergence uh, is crossing certain threshold, if it is by a lot, then in such cases we have to make sure that we uh, uh, properly audit our like of training feature and inference feature to understand why the certain distribution mismatch is happening. Uh, Again, the third thing is that like continuous training and deployment. Uh, Wo- One of the thing like we see in more in recommendation system, that these are like partial observable system, and they sometimes need a continuous training to understand user dynamics and adapt during like inference. One of the changing data generation process we can see in the time series forecasting, where we train our model with historical time T1, and then we try to forecast T2. But we know that like sometimes this T2 does not have same distribution as T1. In such cases, what we do, like some kind of uh, uh, two-phase prediction comparison. In two-phase prediction comparison, what you do, you take your model, suppose you have a historical data T H, and you divide your historical data into two parts such that like you have like a th1 as your historical data, and you try to predict like th2. This is another phase of data. And similarly, you take like in another instance, like you take another history as a t3 ts3 and try to predict th4. So what you're trying to do, like you're trying to understand that historically, if the data changes, how your model is also changing with the change in data, and that will help you to optimize your model for several these instances where there is some kind of like there is some kind of time series shift or some kind of like data drift in your model, and how corresponding to that data drift, how much you are like how much your model is also drifting with your training. So that term known as like continuous training and deployment, where you take like historical data and you create a holdout set, and in that holdout set you continuously improve your model drift by associating it with uh, your training data. Uh, Apart from that, there are some more deployment techniques discussed in this chapter. One is well known, is called ensemble. In the ensemble approach, what you do, like you have like a multiple models, like model 1, model 2, model 3, and rather than taking like one prediction for one learner, you take like some kind of you use like some kind of pooling mechanism where you either average out these predictions and generate a final average prediction, or you give some kind of weightage to these model x1 or x2, and based on those weightage to a certain model, you generate like overall predictions. So these approach are called like bagging approach, where you generate a uh, uh, weighted average of prediction of these different models. Uh, it's such things can also help us to do something called hot swap. What is hot swap? Hot swap is a technique which can help us to understand that how our model is working for different cohort of users. So for one example, they have taken that, suppose you have like, long-term value model where you want to predict a long-term value for your user, but you know that your model works differently for new client, existing client, and active client, right? So suppose you have like three type of cohort, like this cohort one, you have like all the new clients. In the cohort two, you have existing client, and then you cohort three, you have like active client. And you know that like your model works, your ensemble model, that for new clients your model 1 works pretty well, for C2 your model 2 works pretty well, and for, let's say, we have like one more model like M3, right? So this M3 works pretty well for these active user. It could be a combination of several models. For C2 X, like M2 and M3 are working very well. So using this ensemble approach, we can do like hot swap the component, that whenever we see like a C1 model, we can adjust these parameters such that we have a higher weightage to model 1 and lower weightage to model 2 and 3. And similarly for different cohort, we can actually change the weightage of the model to generate better recommendations for user. Uh, there is one more technique I discuss here is called shadowing. So shadowing is like staging in software engineering, where you deploy like two models at the same time. So suppose you have model one, which is your main model, you deploy it to production, and silently you also deploy another model which is called model two. And both of this model will get exact identical user. Uh, it, but this is your production model, and the shadow model, you try to understand that how much predictions are varying for one into another. This actually help you to understand that how much variance there. uh, it can be an identical model, right? There are two identical model getting like, identical users, and if we see that this is for the live users, so this model one is for all the live users, and this is the shadow model is getting all the live user data, but it is not deployed in production. And we can see that how much variance it is generating in these two models. These things can help us to understand that how much variance our model can get when it goes to the production, and is the production data is actually making any uh, some kind of external effect on our model. Uh, s- Similarly, there is another technique which is very common, experimentation, where we run like online controlled experiment, where we have like a model M1. This is the new model M1, and this is like our legacy model M2. And what we do, whenever we divide our total number of, we take uh, uh, a small set of users and divide into like two groups, A and B, and the A will get like your legacy model prediction, and the B will get like your new model prediction. And with that, you will try to understand that how much impact M is making on user B using null hypothesis testing. Now, third thing discussed here is the called model cascading. It means that like sometimes you don't want to just ensemble your model, but you can also cascade your model, right? So in the cascading model, like what we do, we have this some kind of condition which can help us to understand that whether we want to uh, uh, divide this process into a two-step process. So in the sampling, what we do, like the user feature gets to both of the model and we take their average prediction. But in this method, what we do, we first send our predictions to model 0 and understand that whether these predictions are confident enough or not. If we have like a higher confidence prediction, then only we'll go to the uh, we'll only rely on model 0 and we'll just do the system exist. But if we don't get like enough prediction from model 0, what we'll do, we'll go to the model 2, and model 2 will generate a new prediction and will take average of both prediction, right? So what it will do, it will actually ease out a lots of stress on your system, because right now you are just deploying one particular model. As we all know, the ensembles are computationally very expensive, because you are like if you have millions and billions of users, you have like you are deploying two models at the same times, and then you have like higher computational cost. But there are some instances where you have like some easy prediction which can be only trusted with higher confidence with one particular model. And sometime when we get some complex example, what we can do, we can generate some kind of confidence score, and with that confidence score we will send it to model 1, and we'll take a average of both those models for such hard examples. uh, at the last, we'll discuss about the evaluation flywheel. That means we want to evaluate our models on a consistent basis. One of the techniques discussed here is like daily warm start. So in the daily warm start, what you do, like you uh, understand that like for some of the like your cold start user, you have like some kind of data available, and there are some particular user where you do not have to reset their state on a regular basis. what what do we mean by that? Like, suppose you have like some users who have like, high frequency rating update. That means that you have like extremely high feedback available from those users. Those users are very active and they actually regularly provide you updates. So in such scenario, like you don't need to update their ratings every time you get the prediction, because you know that their ratings will not vary a lot, and we have a higher confidence in such. So you only uh, update their rating after like some larger interval. You don't do like regular update of their rating. And you you using this technique, it helps you two ways. Like, first, obviously you are having like some kind of warm start of your system, because you already have like pre-existing rating of user A and B. You're starting from there, and you are also like uh, you are also putting emphasis on your cold start user, where you have like a sparse rating, and you are not updating too much rating of your heavily active users. Um, Another thing is that like we can do that. We can uh, orchestrate our like lambda architecture. So the lambda architecture we discussed in a earlier, that has two parts. One, we call it like a speed layer, and the another fork is known as batch layer. So this batch layer is responsible for the batch training, and the speed layer is responsible for the streaming data and inference. So here we get like all the streaming data. Here we'll get like all the batch data from our feature store, and we uh, we can orchestrate this process to understand that if we have like data coming in the small batches, then only the speed layer will be responsible for such task. And whenever we have data coming for in a large volume, then we can send it to the batch layer. And for that, we need like some kind of orchestration tool. And this GOCD, Metaflow, and Kubeflow, these are like some of the tools that can help us to orchestrate those tasks. Uh, Logging is also a very important part of evaluation flywheel. We should make sure that we log like all the important steps in our recommendation system. Uh, One of the important, like if we talk about different stages of recommendation system, we have like something called collector logs, filter logs, and ordering logs. And if we understand our multi-stage recommendation system in the first stage, we actually our collector actually collect all the important candidates from our database, and then it send it to like filtering and scoring, where it actually rank those uh, collected candidates for us. In the third stage, we actually apply all the business logic in serving layer to send it to our user finally. So in each step we should have like appropriate logging. One of the important thing discussed in this entire logging thing, that we should have something called this correlation id. This correlation id will help us to stitch all these logs together from end to end. So individual logging is important, but sometimes like we need like a aggregation of logging to understand that what is happening at a certain stage. And in such cases, like this collection correlation id can be very handy, because take example of the collector log. Suppose we have a certain user id for which we are like generating like a nearest neighbor search. Now we want to understand that if the nearest neighbor is generating enough embedding for each and every user id, and where are some of the instances where it did not generate the user ID. Uh, we can also see that like by generating like a lower density like embedding, what is the impact is going on the filtering and ordering stage. And to understand like how these like how the entire workflow worked for that particular user, we have to have like this kind of correlation id, which will help us to uh, track that entire life cycle of that user i- i- in this particular process. And it will also help us to understand that if we apply like other criteria, like applying bloom filter to eliminate potential bad recommendations, uh, we are augmenting certain features like item and features, and we are scoring our model, what is happening for individual users at every stage. And when we apply a business logic, how much it affect certain users or certain items. And all this can be possible if we have like a proper correlation id, because this correlation id will help us to track all those information and stitch it together and view it in an aggregate level. There are like various software available that can be used. uh, so suppose to indexing, we can use like Elasticsearch. Uh, uh, to in, to handle the incoming log, we can use this log stash, and we can use Kibana like software to get like higher level UI and dashboarding of our logging. At last, we discuss about the active learning. So active learning says that like we should not only rely on like implicit feedback from our user, but we should also harvest the relationship between data and observation. It means that we already know from previous lecture that like Matthew effect is well, one of the like detrimental impact, having a very detrimental impact on recommendation. What is Matthew effect? Matthew effect is just like some this is a like a popularity bias, where some content, like let's say this is a distribution of our item, some small fraction of our content have extremely higher usage, and these are like very popular content, and large catalog of our content we had like very low usage. And in such cases, what we can do, we can actually use boost our new content using this active learning approach, where what we are trying to do, we are trying to boost our new content to our user. Now, how we will do it? We can do it like in a simple example. What we will do, suppose we can write a certain kind of rule, where suppose if we have a new content C, we will actually uh, show it to our user for like for n number of days initially. So suppose for first 2 days we will try to surface a new content to our user, And once we collect enough feedback from our users, suppose we have like getting like at least uh, three number of clicks for n number of days. So suppose we want to surface this content for next 5 days, and we want to gather at least three, or we want to surface it at least five number of days. And if these thresholds are met, we actually try to understand the log loss between like the newly surfaced content and already present content. And based on that, we will understand that how much impact this new content will be making on our user. So based on that, what we can do, we can have like two types of optimization. One is called local optimization, which actually increases personalized content. And another is like global optimization, which is used for non-personalized content. Both of these meaning that like if we want to like personalize individual user, uh, we would like to look into these metrics like primary prediction, influence based rating optimization, or user segmentation. And when we want to like improve overall like uh, recommendation system for non-personalized way, uh, we would like to optimize these different metrics like popularity, entropy, greedy extent, co-coverage, and user rating variance. So active learning will help us to understand that what segment we want to divide our user and what type of optimization goal we have. Do we want to do like user level personalization, or do we want to do like global level, or like all user based personalization? Now moving with the chapter 8, here we will discuss about whatever we discuss in last three chapters, we'll try to implement here using various of tools and frameworks. So here we will be using these five different method. First, what we'll do, we'll understand how we represent our data using protocol buffers. Now we'll discuss about data processing frameworks. We'll take a PySpark sample program, we'll convert it to a Glue embedding, and then finally we'll learn some techniques in JAX, Flex, and Optex software to how to implement this overall like program in for retrieval. So first, like what we are trying to create here, we are trying to create a system that recommend words from Wikipedia based on co-occurrence. That means suppose you have like uh, you have like all the Wikipedia corpus, and you want to train your model from all the Wikipedia corpus to understand that suppose you have certain word W1 based on their co-occurrence in the corpus. Suppose how they like how much they occur with each other, right? This word one is co-occurring with W2. Based on this learning, we want to recommend like similar words to user. So suppose we have a new word WN, we would like to recommend like some uh, new like this WN1 to our user based on the model that we train on like co-occurrence of this Wikipedia word. So for that, like we use like different tech stack. This tech stack actually help us to understand that how we build like large scale system, how we build like uh, basically a retrieval system. So primarily, first we try to understand what is protocol buffer. So protocol buffer is a program that can help us to read and write binary data in a structured way. It is much better than like existing data structure like JSON, where we don't have like uh, strict type mechanism, and there is a like a less way to serialize that data. We have like a big data, we will be using a big data framework called PySpark, which actually help us to process large amount of data on distributed cluster. We will use TF-IDF method. Now TF-IDF method help us to understand how importance of a word in a document. That means that it means that term frequency inverse document frequency, that how many times a word occurred in a document and how many document this word has been occurred. And this will help us to understand what is the importance of this word. So suppose we take a trivial word like the. So the will occur a lot in one particular document. But if we see like n number of document, for all n number of document, the will appear regularly. And with that, like it will get like a low importance score because it is both numerator and denominator both are like pretty high. Suppose we have like a some important word like, let's say, deep learning, which is very highly used in one particular document, but it is not present in another document. In such cases, deep learning will get higher weightage. Now, why we are using PySpark, as it is already designed? PySpark is a distributed computation framework. It uses something called RDDs, which help us to write like stateless function. These stateless function help us to distribute them over multiple Spark cluster, and with that, like we can apply lots of uh, operations that can be parallelized and can run on like multi-core machine on multiple clusters. Very simple task. If we can see that, like suppose we take an input file, uh, this any input file I, and we want to apply this anonymous lambda operation, which actually convert every word into lower characters. This entire operations can be applied on RDD, so it can be our what we say like PySpark con- controller will distribute it among multiple workers, right? Uh, so in the simple program, what we'll do, we'll try to create a like a title and token dictionary. And what we are trying to create here is just we are trying to create like a two dictionary. So one dictionary will contain like all the words, sun W, and their count, C1, and then we'll try to create a document along with their count. So uh, this is like pretty simple program, like just we are here, we are like defining our flag to take like input files. In the second program, we create this token dictionary. In this token dictionary, we'll take a text document and we'll convert it to like a token to count hash map, whatever you can say. And similarly, we'll create like a title dictionary. Title here means like a entire document, and based on that title document, we'll create a like a tokenization of title dictionary. And this is the program we have written. Uh, it looks like a lot, but on a very high scale, what it does, it actually create those uh, different like tokens for us, and we are just dividing it just into different subroutines. These every of these functions which utilizing protocol buffer to generate like every tokens of our dictionary, and we'll see that dictionary how does it look like. So what we'll do, yeah, we'll take the question in the last, so I can stop the recording. So what we are trying to do, we are trying to create a like a co-occurrence matrix. A co-occurrence matrix you can see is as a sparse matrix, where we have like every token available I and every word available J, and we try to fill this matrix such that we try to understand that, suppose this I, this J occur at like at number 2 position, how many number of times. So how many number of times this particular word J occur co-occurred with I, along with their frequency. And using this particular representation, it helps us a lot. So in this entire method, what we did, we used like protocol buffers. Now what does protocol buffer does, like it actually serialize your entire document, because we are talking about like around 21 GB of Wikipedia content, and I run on my laptop. It took more than like I don't know, an hour to run, to just collect the data and like do all those things. So what our protocol buffer is doing, like it actually creating this long series of uh, partition, These long series of partition, we can apply the entire mapper operation. Suppose the entire map operation is like, count the words and like create their uh, frequency. So suppose a word one, and we want to create like how many times this word one occurred in this document. And what protocol buffer will do, it will take this, it will create a like a very long, like let's say 64 MB of entire serial of that document, and apply map operation on that document. And why we want to do it, because in Spark like cluster, the communication between like two nodes are most expensive operation. So network bandwidth is the most expensive step here, and that is the most time consuming, where you have to like send your data from one cluster to another cluster using a bandwidth. And if we apply a mapper operation on a worker node itself, it is the fastest way to get that count, right? So what it does, like it on the worker, it takes very long partition, and on those long partition, it is applying those like uh, word counter frequency operations. And using those one counter frequency operations, in the reduce step, it has to do like lower work uh, while fetching the data from the network bandwidth. So we are allocating a tedious task to these workers in a like long format and in a mapper fashion, that in the map reduce phase, in the mapping phase, like we have like this long partitions has been created, and we are applying the lambda operation there. And during the reduce phase, what we are doing, we are just collecting and counting those dictionary from one cluster to another cluster, right? So this is like classical map reduce operation, but using this protocol buffer and like this hashing technique, we are optimizing it on a even on a small like single machine, rather than needing of like very high memory or high computational machine. So what we generate this called this sparse co-occurrence matrix, where this I is represented by this index 1, this j is represented by this index 2, and the count is represented by this index c. So this c, this is j, and this is I. This is like a sparse representation, because if we design this matrix will be a huge, because we have like lots of words and lots of like co-occurrence of this words. So this is like uh, very compact representation of those uh, co-occurrence metrics. And once we generate those co-occurrence metrics, we actually reverse sort this co-occurrence metrics based on on their count frequency. And why are we doing it? So the simple way to understand it, like suppose once you generate that dictionary, if you reverse sort it, that means in the descending order, the higher frequency words, suppose this one has like 1 million occurrences. So this word will occur at this word will be located at earlier index, and the larger index will have like lower occurrence words. So suppose this wn has like a word count frequency of like 2 or 1. So in this manner, what we have like a extremely large space, like saving of our like memory space, because we are not allocating a very large integer for a high frequency word. We are uh, allocating small integer for high frequency word, and we are allocating uh, very small memory for this like a low occurring word. And once we do that, we can actually use this co-occurrence matrix to build an MPIR recommendation system, the most popular item recommendation. And how do we do it? Like it's very simple. So suppose that like the comes with like let's say rock, right? The rock, right? I'm just making up this example. So that like the and rock like comes together a lot, and they have like very high co-occurrence matrix. So whenever like you have like a word the, you can look up your like sparse matrix and generate like a next word for you, and that the and rock comes together many times, so you recommend rock to that word. and that is how you generate like most popular item recommendation based on high frequency using just this matrix. Even with the simpler matrix we can actually generate like most popular item recommendation, but we want to go like little further. And what we will be doing using this sparse matrix, what we will do, we will, this sparse matrix is a high rank low density matrix. What we call it, high rank low density matrix, LD. That means that it has like very large dimensions but very low less data inside it. What we will transform it to a like low rank high density matrix. That means what we will convert it to a like compact representation, which will have like higher density but very low rank. And doing that will, this process is basically called embedding, classically embedding, like which is used in across all the machine learning. So what we'll do, we'll convert this sparse matrix into a low rank high density matrix, and we will be using this globe embedding. So what does globe embedding do? This, the objective function of this globe embeddings is to find out uh, this one, right? So to find out these two vectors xi and xij such a way that their dot product is maximized when they have like higher co-occurrence. So suppose, I think there is one thing is chopped off. I think there was an equation written here. So what it does, like we want to create this xi dot, like let's say this is dot product xi dot xj. So suppose we want to create those embeddings xi and xi such that their dot product is high when we have like higher occurrence count, like n. So n is the number of time that that word count together. And what it is doing is that like rather than relying on that sparse representation, we are generating our own embedding where we just need these like two embeddings of those words, and when we multiply those two embeddings we'll get a number, and based on that number we'll understand that how much co-occurrence is there between these two numbers. We can also generate like features of these embeddings. So features mean like this other dimensions. Suppose we have this like one dimension thing, but we can also create like some other dimension using like features. And for this feature we can use like min hash technique. uh, Min hash technique is nothing like, suppose we have like some word like zebra, right? So what we can do, we can take like this first four letter or first five letters and hash it to a like a function and generate a hashing x. So whenever we get like another word like zebra crossing, we will also take only 4 5 words of this one, and the zebra crossing will also be hashed at the same function. So we'll reduce the dimension and we'll combine them into like one encoding. Now this method has its own flaw because we know that zebra and zebra crossing are completely unrelated things. But just for some, let's say for some application, it might work. So what we are trying to do, this is our target. We are trying to generate here at 1 plus log 10 n. The one we are adding just to avoid like a log 0 thing, like where we have 0. We would like to uh, we have like some weight just to penalize like high frequency words. So suppose if we have like high frequency word, we will penalize them, and we'll generate this loss function where we have this h predicted and h target. So h target is already given for a word, and h predicted will be generated by this equation. So suppose we have like the embedding of I, embedding of J, and we are introducing two bias term to remove like popularity of like I and J. So if I and J like higher popularity, this bias I and J will soak up that term. Once we complete that, we'll write this program. This program, what we'll do, is a simple program. It will just try to optimize this loss function and generate like a embedding for us. And once we complete this embedding, we can see that like for word democracy, it is actually generating like some recommended word, right? And these recommended words are very like very relevant to the word we generated. So it's a item uh, recommendation where we have one particular item and we are finding similar item or a recommended item. Obviously, the first word you'll see most of the time is the same word as a higher relevance with the query word itself, but it's not true all the time when you have like popular word, because sometimes there is a cases where you have a query and you will get a popular word at the first preference. So with that, I will just conclude this talk, and in the next chapter we'll discuss about chapter 9 and 10, where we learn about how to rank and how different types of ranking and how to use different type of metrics for personalized ranking of recommendation system. So yeah, see you next time, and I'm stopping the recording now.